Hey guys, we're going to finish up 1.1 today, and we're going to talk about surface area to volume ratios, and we're going to talk about magnification. So make sure you are looking at the skills and understandings for the proper section of 1.1 in the applications as we go along, and make sure you're taking those notes because you will have a little review activity at the end that's going to ask you to do some of these things, okay? So just as an introduction, remember, cells come in all shapes and sizes depending on the species of the organism that they grow in and their specialization. But there are limits as to how big a cell can grow. So when we think about all the way down on the molecular level, here we have atoms, which are super, super small, right? And then we start getting into the range of those macromolecules that we talked about. So lipids, proteins, enzymes, carbs, right? So there we're talking about anywhere between a nanometer and 10 nanometers. And then you get to the stage or the size of a virus. Now, viruses, this picture looks like it's as big as these pictures, but that's misleading. So viruses are very, very small. They're collections of macromolecules that are kind of sealed in an envelope. They're much smaller than cells. And that's because they invade cells, right? So viruses are very, very small. If a typical bacterial cell that you find on a desk was the size of an apple, that virus would be the size of a pinhead. So viruses are very, very teeny, not much bigger than the macromolecules that make them up. Bacteria, on the other hand, are quite a bit bigger, and you can consider some organelles to be on that same size because mitochondria and chloroplasts, they used to be their own prokaryotes, their own single-celled organisms, right? And now they form symbiotic relationships with us. So they're about the same size as bacteria. And then bigger than prokaryotes, we have eukaryotic cells. So remember, prokaryotes are pretty much bacteria, right? And you are a eukaryote. So now we're talking about plants, animals, fungus, things like that. Their plant animal cells are quite a bit bigger than most bacterial cells. And then you get to the size of zygotes, so a human egg, and that makes sense. It's got to be bigger than one animal cell or plant cell because it's actually two cells. It's a sperm and an egg, right? And then you have now you're getting into the range of you can see stuff with your eyeballs, like frog eggs, right? And then bigger stuff like chicken eggs, ostrich eggs, which technically we consider to be a cell, one giant, giant cell. And then, humans, right? So just as a refresher for scale, when we're looking at light microscopes, because in this particular topic, in topic 1, you're going to start doing sketches of microscope drawings. When we're talking about light microscopes, which is what we use, we're talking about we don't see any viruses. We're not going to see any viruses that are with a light microscope, but we will see certain kinds of bacterial cells and we will see plant animal cells. And so remember, cells, vast changes in size, large and small, but they do have limits. So this is understanding number 3. Surface area to volume ratio is important in the limitation of cell size. So a cell's volume determines the amount of chemical reactions that can take place in its cytoplasm. Well, that makes sense. A cell's volume, how much room there is inside, depends or is, let me rephrase that. I'm just drinking my coffee, so bear with me. A cell's volume is important. The more volume there is, the more reactions can take place inside. These reactions require the import of reactants and the export of waste products, right? So that surface area becomes important in terms of getting materials in and getting materials out. Thus, the higher the volume or the bigger the volume, the faster resources are consumed. Well, that makes sense. I mean, the bigger you are, the more you want to eat, right? Sort of. A cell's surface area determines the rate at which molecules can pass through the membrane. If there's more surface area available, more reactants and more products can diffuse in and out of the environment. Well, that makes sense. The more space there is for the cell to have contact with the extracellular environment, the more opportunities there are for things to come in and out. So cells with larger volumes they require more precursors for the metabolic reactions, right? If they are bigger on the inside, remember, they're going to need more of those chemical reactions. So they need a large surface area to get that stuff in. Now, you might be thinking, well, like, what's the big deal? Is if you have a bigger volume, then by definition, you have a bigger surface area too, right? Well, there's a ratio there. So it's not like the TARDIS where like the inside is bigger, but that volumetric relationship, that proportional relationship, it has limits. So as a cell grows, its surface area, SA, and volume don't increase at the same rate. A high surface area to volume ratio is essential for cells to survive. So let's think about perfect cubes, right? So here's one. Is that a micrometer? Picometer? Micrometer? It's not a micrometer. 2 units in size, 3 units in size, 4 units in size, 5 units in size, 6. Now remember, volume is going to be cubed, right? So 1 cubed is 1. 2 cubed, 2 times 2 is 4, times 2 is 8. 3 cubed, 3 times 3 is 9, times 3 is 27. So you can see we went from 1 to 8 to 27. That's kind of staggering when you think about the implications in terms of the requirements of the cell. Remember, the bigger the cell, the more products it's going to need to make and the more reactants it's going to need. So for each step up, you're requiring a lot more materials to keep the cell alive. That's going to be a limitation. Okay, so I want you to try and fill this out yourself. So here we have the size. We're going to consider our cells to be perfect squares just for a cube for the sake of argument, right? So here we have the length of one side, right? Here we have the surface area. And here we have the volume. And I would like for you to put this table in your notes because when you're going to be doing the activity later and you're going to be like, I need to figure this out. How do I do it? You're going to have an example. Remember, surface area is 6 times whatever the side is because a cube has 6 sides, right? Top, bottom, and then the 4 around the edges. And then volume is going to be S cubed. So you can pause it and finish your table, right? And let's figure this out. Okay. So if a side, and let me draw a picture. Let me draw a cube just... That's a bad cube, but whatever. You get the idea, right? So the surface area is 6 sides because there's 1 on top, 1 on the bottom, and then 4, 1, 2, and the 2 we can't see, right? So if each side, let me do a better one. If each side is 1, right? Surface area is going to be 6. So for our first one, our surface area is going to be 6, right? And then our volume is going to be 1 cubed, which is 1. Okay, so for 2 surface area is going to be 24, right? Why is that? How come it's not just 8 or 12? Or I need some coffee. Hold on. Let's do this again. Oh, I got it. Right. Just needed a sip of coffee. Okay. So 2, 2, 4. Okay. Surface area. 4 times 6 equals 24. Okay. 2 cubed equals 8. Alrighty. Let's do another one. 3, 3, right? So 3 times 3 equals 9. 9 times 6 equals 54, right? 3 cubed equals 27. Do you get the idea? Let's do 4. 4, 4, 4 times 4 equals 16. So that's the surface area. Surface area of one face is 16. 16 times 6, because we have 6 sides, is 96, right? 4 cubed is 64. Let's do it again. Let's do 5. Okay. So we have a cube. Its height is 5. It's a cube, right? So 5. So the surface area of one face, 5 times 5, is 25, right? Now we have 6 faces. 1, 2, 3, 4, 5, and the one in the bottom is 6. Okay. So 25 times 6 equals 150. The surface area is 150. Now, 5 cubed to get the volume is 125. Okay, last few. We have 6. 6 times 6 equals 36. 36 times 6 is 216. 6 cubed is also 216. Look at that. Love when numbers work out. And then the last one, 7. I guess you could just use squared, right? 7 squared equals 290. Or I don't know what 7 squared equals. I should know this. I have a 5th grader. No, I have a 4th grader. I just helped her with the multiplication tables. What's 7 times 7? Well, 7 times 5 is 35 plus 14 is 49. Oh, I should know that. Dumb. Right? 49 times 6 equals 294. And then 7 cubed. 7 cubed is 343. 49 times 7? Yeah, I guess that makes sense. Okay. All right. So now that we know how to get all those numbers, let's just distill this and make it really easy. Okay. So you take the size squared times 6 to get the surface area, right? And then to get the volume, it's the surface area cubed. And that's right here. But this, we had to remember this part, right? To get the surface area, you have to multiply this by itself. So squared, 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 squared. Times 6 to get that, times 6 to get that, times 6 to get that, times 6 to get that. Okay. And then we had to get the surface area cubed for the bottom. Okay. Oh, now we got to do the ratios. Surface area to volume ratio. Okay. So surface area to volume ratio. All right. Surface area is going to be 6 to 1. Or another way to do it would be what? 6 over 1 would be 6, right? So 6 over 1. 24 over 8 gives you 3. 54 over 27 gives you 2. Over 64 gives you 1.5. Over 125 gives you 1.2. Over 216, look at that, perfect. And then over 343, for the first time, we're getting a surface area to volume ratio of under 1, okay? So you're probably like, all right, this is not a math class. Why are we doing all this stupid crap? Well, it's to show you how the surface area to volume ratio changes. That's why we're doing all this. So here we're going to graph the surface area to volume ratio compared to the initial side length. So remember our cube. It's not a cube. It's a rectangle, but we're going to pretend it's a cube. Right? We're going to look at how this difference changes, right, in proportion to the inside. So does the inside get bigger faster or smaller than the faces? All right, so we're talking about, does the inside get bigger faster or smaller than the outside? I know that sounds weird, but it's a thing. So think about it. I think we talked about this freshman year when we talked about like the elephant and the mouse, which one has greater surface area, the elephant or the mouse, and which one can dissipate heat faster because it had more surface area, it had more skin touching the outside. Well, let's just graph this and find out. We're going to take those same points that we just calculated and we're going to graph them. And here you can see there's a pretty steep decline in that ratio, right? So when your side length is small, the surface area to volume ratio is very, very high, meaning you have lots of outside compared to your inside. Let me say that. So lots of outside, lots of skin, lots of surface compared to inside, right? But the bigger you get, you have not so much outside compared to inside. All right, so this means your insides are very, very big. And this is where you start to have problems getting enough materials in and out. So you can think of like surface areas as like the door to get stuff in and out. The more doors you have to get stuff in and out, right, the better off you are. But as your outside gets smaller compared to your inside, that's not a great idea because your inside, the bigger your insides get, the more materials you need. So this is why this is a limitation on space. If your insides get very, very big, the math says that your outside doesn't get big at the same rate. So you're not going to be able to get enough materials in and out through that door. So this is why cells stay small, because that surface area to volume ratio is important. They need to be able to get enough materials in and out to maintain life, those metabolic processes, right? So it's important that their insides don't get too big compared to their outsides. See, here we go. To maintain a high surface area to volume ratio as they grow, cells have developed a bunch of different adaptations. So first thing is when their insides get too big, they divide. right? So here you have one large cell, right? And its surface area is 5,400, is it microns? I don't know, remember what that is, right? So the surface area to volume here is going to be very, very low. It's got lots of inside compared to its outside. But if they divide, they can maintain that same volume or close to or even more volume, right? But they have lots more surface area to get things in and out. And they can change their morphology. They can change their shape to increase their surface area. So we'll talk about these guys in particular when we talk about human digestion. These are villi and microvilli in your intestines. These are like the little fingers that absorb all the nutrients in your food. And you can see they are long and skinny, and they increase the surface area of your intestines by like 10 times, right? So imagine if you had 10 times more guts in your belly. You'd have to be like a lot bigger, right? But just having these little guys in here, you can have 10 times the surface area that you would normally in a smaller space. And then skin cells, right? They flatten themselves out, become very, very thin to maintain that high surface area to volume ratio. Lots of surface area, not a lot of volume. Lots of ways to get stuff in and out. Lung cells and the roots of plants, they form branches, and that gives them more surface area. It gives the lung cells more access to air, and the plant cells more access to water. You can think of it this way. So, how about I think I have a good idea to explain the surface area to volume. Okay, check it out. So, say you are a thing that needs to get to the center of a cell. Okay, say you're a virus and you're trying to get to the nucleus of a cell, right? So, if you're on the outside, it's going to take you a lot longer to travel this distance, right, than it is to travel this distance. That's why surface area to volume is important. Okay. So review, what role does volume play in cell activity? What role does surface area play in cell activity? Why is maintaining a high surface area to volume ratio important for cells? And what are some of the ways that cells have adapted to maintain a high surface area to volume ratio? You should be able to answer all those questions at this point. And if you can't, you should go back and look at the notes. Also, if you look for Khan Academy, Khan Academy has a really good explanation. If you search Khan Academy surface area volume cell, it'll pop up. I didn't want to play it for everybody because dude's voice kind of puts me to sleep. But if you need some backup, that's a good source. Okay. Next section, we're going to talk about magnification. So you already did the microscope lab and you had to multiply the ocular lens piece times the objective lens piece to get the total magnification of what you were looking at. Well, now I'm going to teach you how to calculate magnification by looking at the image itself, right? So a lot of times you aren't the person looking through the microscope, but you're looking at something and you have to know what the magnification is. And I'm going to teach you how to figure that out. Since cells are so small, we need microscopes to visualize their structures and their properties, right? And 1.2 is when we really start getting into using the microscope and replicating what you see through the microscope. If I'm not back, we're going to do that virtually, so you don't have to mess with the microscope itself, but we will give you really nice microscopy images to work with. Okay, so skill number 1. Calculation of the magnification of drawings and the actual size of structures and ultrastructures. Guidance. Scale bars are useful. And remember, you can always create your own scale bars. So I encourage you, when you take the IB exam, you're going to need to bring a ruler with you so that you can create your own scale bar. So when looking at images, magnification is often stated, indicating the scale of the image. So it could be stated directly, like 250. So you can see here is a fly's face. Yep, it's a fly's face, right? And you can see 400x, right? It was magnified 400 times, and it also has a scale bar here. So it can be one or the other, or it could be both. These numbers, this number, the magnification number, and the scale bar are related. And you can use those numbers in an algebraic equation to figure out total magnification if you have one but not the other. So, when viewing an image in a microscope or a micrograph, magnification can be calculated using the following formula. The magnified size divided by the actual size. Now, this is the actual size of the thing that you are looking at in real life, not in the picture. That's why it's actual size. Okay? So, magnified size, length of the scale bar provided, which can be measured with a ruler, and the actual size represented by the scale bar. So, do you think you can figure that out? Magnified size, the length of the scale bar. So, like, say the length of the scale bar is 50 picometers or micrometers, right? And the actual size represented by the scale bar, and that would be like an inch. Okay? Got it? Okay. So, practice. What is the magnification of this image? Note that the value will change depending on the size of your screen or printout. Okay. So, this is 5 micrometers. Since I'm doing this on the computer, let's do this way. Okay. So, what I'm going to do is I'm going to say, can I still draw on my screen? Yeah, I can. Okay. I'm going to say that this little line right here, I'm just going to make a number up. I'm going to say it's 5 micrometers. I'm going to say that that's 1.5 centimeters, just to make it easy. Okay, now I'm going to take, because I don't have a ruler, so what I'm going to do is I'm going to make a line that's exactly this length, and I'm going to make it, I can use a bracket. Why don't I use a bracket? It's probably better. Okay. There we go. And making sure that it's exactly the same size. Even though this is just an example. Okay, good enough. Okay, so this is our example bracket. Now, I need to figure out how many of these this is across. So I'm not going to change it. I'm just going to a whole bunch. 1. 2. 3. 4. No. All right, now that's not like the widest point. So I need to like rotate that so that I'm looking along the widest point. We're going to group those together so they don't. We're going to. Now I'm not changing the size. I grouped them together just so I could move them together. I think I can fit one more in there. It's a little short. Almost. Okay. So how many was that? 1, 2, 3, 4, 5, 6. We'll say 6.9. Okay. So we had 6.9 of those brackets, right? That were supposed to be 5 micrometers each. All right. So we said that our magnification was the magnified size divided by the actual size. Okay. Right? So the magnified size was, we said, the length of the scale bar provided in the image, the length of the scale bar, which can be measured with a ruler. So that would be our 1.5, right? So 1.5 times 6.9, because that's how many of them there were. One point five times 6.9 equals, nope, 10.35 divided by 5, right? Because our 5, this is our 5. That's the actual. So our actual was 5. So 10.35 divided by 5, it's going to be just over 2. Okay? So our magnification was just over 2x. Okay. Now you can rearrange that to give you a couple of different things, right? So you can give the given scale length. Oh, I don't need that. The given scale length divided by the measured length of the scale, right? So we measured the length. So the measured length of our scale we said was 1.5, and the given scale length, if you have it, that's equal to the actual size divided by the size in the image. Or actual size equals size in image divided by magnification. So you can rearrange this any way you want. It sounds kind of complicated. Let's do another one for practice. Okay, so here's this thing, right? How long is the cell in the image below? So 10 micrometers. All right, so let's make sure we're using the right terminology. Actual size represented by the scale bar. So this 10 is our actual size. Okay. Now, is that right? Am I doing it backwards? Actual size. Actual size represented by the scale bar. Okay. Magnified size. Length of the scale bar provided in the image, which can be measured with a ruler. So our magnified size is, if I measure this with a ruler, I'm going to make it easy and just say that it's 1. Okay. So this is our magnified size. Okay. Now, let's see. If I were to make a bracket, no, I want to keep those. Actually, let's copy one of these guys. Let's make sure it's the right size first. Okay. No. Can I lock this? Sorry. It's just going to bug me if I keep moving it. No, I don't want to. No, I don't want to do that. All right, well, whatever. Good enough. You get the idea. I guess I'll just do it this way. Ideally, those would be in a straight line. I realize it's not in there, but that's okay. All right, so let's see. Just short. So, actually, I could probably move this over a little bit. 2. All right, there we go. That's pretty good. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 9 of these. 9 scale bars, right? So 9 scale bars would be 90 micrometers long, right? So it's that. We measured 9 across. 9 times 10 is 90 micrometers. Okay? That's not hard. And then if a red blood cell, let's see, has a diameter of 8 millimeters, and a student shows it with a diameter of 40 millimeters, meaning like the image, right? And a drawing. Well, you might be thinking, if it's only 8, why did the student make it so much bigger? Because the student's drawing it on a sheet of paper so that you can see it, and this is the actual size, right? That's why. What's the magnification of the drawing? Okay, so if the actual is 8 millimeters, so that's this, in real life, that's the size, and they drew it to be 40, right? How many times bigger is 40 than 8? It's 5. It's 5 times bigger. Yeah, got it? Okay. All right. Well, hopefully, I'm going to give you some questions to work on, and you can work on them together with your classmates and see if you get them right by the end of the class. All right. Thanks, guys.